There's some pretty interesting Ozark geology in this fresh foundation site, and in the soaring walls of this active quarry. We were invited to visit both sites by an enthusiastic viewer who wanted to learn more.
So we're here in Morgan County, Missouri on the site of a new home excavation. And Walt invited us over here to take a look at this pretty cool site. Walt, why was this so interesting to you?
When the excavators got done with their 2 weeks of work down here, I was amazed at what I was seeing, but I had no idea what I was looking at. I said, I need some experienced eyes to come and help me on this. And that's why I knew your site. I've enjoyed Ozark Outsider and said, maybe Eric could help.
Cool. So we're going to take a little bit of time to walk around Walt's site, and Walt's agreed to film some things we're looking at. So hopefully you'll come along and enjoy this kind of neat look at a site that most of you will never see, because in a few more weeks, this is going under concrete.
Tell me a story.
Walt took a lot of footage for his own use, but also gave us permission to cut together some highlights to share on the channel. Exploring and teaching in person is such a different experience than producing videos, and we really enjoy doing it. We thought viewers might enjoy seeing a site visit like this, which is also a chance to see how we try to study and interpret a new site in real time. So, with thanks to Walt, let's explore some highlights of what he brought us to Morgan County to see. Just for reference, everything shown in this video occurs within the Ordovician-age Gasconade Dolomite.
So what we have here is some breccia, which is a geologic term for a rock that has a bunch of broken angular fragments. And you were wondering if there's a chance that that could relate to the Osceola-Wobolo impact. So Missouri has 3 impact craters. 2 of them are poorly constrained in terms of the time. The Wobolo one is actually pretty well constrained to Mississippian age, 300 some million years ago. This is early Ordovician, so at least 100 plus million years before that. So definitely not related to that.
So you might have deposited a bunch of limey layers of limestone, dolomite, that kind of thing. But if you expose this to air and you start developing a bit of a landscape, little river channels, right? Think any gravelly Ozark Creek bed, right? You do that, you fill that in, then the sea level goes back up and you deposit more carbonate layer. All of a sudden you've sealed in these little pockets of other material. So it's possible something like this is some little pocket like that. The other possibility is, we talked about paleokarst. We could also have, after all this rock was developed, we could have dissolved in, a little piece of cavern here, even a small one, just a little pocket in the cave, and then through, say, a sinkhole on the surface, stuff got washed in, a flood washed stuff, filled that in, and so maybe this is all jagged stuff that washed in much later.
So one of the fun parts about geology is both coming up with these ideas and then looking for clues that either support or, refute certain ideas, because it's always good to have, the more ideas you have of possible explanations, the better. I will point out one thing that maybe argues against the channel idea, although I like it, is the way this bulges up over here. If with a channel fill, you would expect the bottom to be kind of a rugged surface, but then the layers that deposit over that you would expect to be nice and flat. But we have this weird ragged bottom, but then we have this like rugged, jagged top to it over here. Is that making sense?
Yeah, so what she's saying is a channel that later got covered over would have a flat top like this and only bulge down. A paleokarst would be a hole in the rock, so it would bulge all over the place. And here, there's definitely not a flat top. This kind of has a much more rounded, kind of bulbous look that implies that it dissolved throughout the rock, not that it had its top cut off as a channel.
The contact that's really uneven up at the
So that implies, leans toward the paleokarst idea that this is an old coal small cave rather than a river channel at the surface. If you were given an encyclopedia, for those of us old enough to know what an encyclopedia is, if you ripped out 80% and then put all the pages and rebound them into a new book, you'd have a lot of information, but you'd be missing huge chunks of knowledge. That's
Good description.
That's what the geologic record is. What we can see tells us things, but what's been ripped out or never got written. Let's say there's a printer error and half the pages never got printed in the first place. And so 40% never got printed, 40% got ripped out. What we're left with is 20%, and we're trying to reconstruct a full story from that 20%. So it's fascinating, but you are missing things that you simply don't have evidence of. So some things like this, we don't know. You may not know because there isn't enough information left around it to explain it. Trace a layer right here, this kind of clay layer.
Continue.
Notice how the roots are really preferentially coming out in that layer.
Yeah.
There's no roots up here or down here. They're all coming out of this.
And above your head too.
Yep. But again, there's, that one's coming out of another one of these clay layers. with these thin clay layers in the bedrock, the roots are going down vertically and finding those and growing sideways because the rock's softer in those clay layers. So you're absolutely getting these zones of root movement, both because it's easier to move, but also because that's where the water is.
Yeah,
The water moves through there too, so the roots are following the water through these parallel semi-horizontal clay zones.
Yeah, all the way down here. Yeah, all the way down here. There's still roots. Everywhere I look along that way.
That's a really fun biology-geology combination.
Tell me that again, please.
So there's lots of normal dolomite down here, you know, your carbonate rock, marine, shallow marine, but up here there's this beautiful layer of sand, very sandy stuff. There's actually another one down, distinct one down there at the base. But you know, you can basically, I can crumble this in my hand. It's it's soft sand. See, I can be all Iron Man and just crumble that. It's beautiful sand. So this, you know, this kind of thing would represent again a period where the sea level went down a bit, and this is a little bit exposed. Maybe it's a beach, maybe it's a river channel. It might even still be underwater, very shallow. So this doesn't have to be above water, but it's an especially shallow situation. Whereas the dolomite, you need deep enough water for there to be marine life, you know, reefs and things forming. This is very, very shallow, near beach.
How would you explain what's going on there? Tell me a story.
It's a fill of red clay, essentially. When this kind of dolomite limestone...
At this point, wind started to be a problem for the audio capture on Walt's camera, but we weren't done. We looked at the very uneven upper surface of the dolomite bedrock, and how it was filled in by a thick layer of red clay. This is pretty common in the Ozarks, since clay is often left behind as carbonate rocks dissolve away.
Heck, tell me a story.
Alright, so we were talking about why we get...
We talked about how alternating layers of different rock types, like the dolomite and sandstone seen here, can be produced by a variety of factors, from sea level change to local environmental conditions like storms.
Eric, tell me about that chert.
So chert is super common in the Ozarks.
We discussed how chert forms, either initially from silica-rich mud or later from silica-rich groundwater, and why it might be concentrated in distinct layers like this. We explored fun things like Ooids in a historic cabin next door, and a beautiful stromatolite in Walt's rock garden.
And we still have related stromatolites growing today. There are parts of Australia that you can still see these today. So
we looked at patterns of parallel joint fractures in the rock, and the occurrence of minor faults as suggested by the presence of slicken line textures that preserve evidence of movement.
This is really common in minor faults. It's sort of a shear. All the shear of this, the friction, kind of grinds and reblends it into a new material. That kind of flat stuff in there really looks like something you find when a fault kind of pulverizes everything and reforms it in a smeared out.
Yeah.
Like you took two things of Play-Doh and smeared them, you're going to get that kind of linear stuff right against the smear.
Excellent.
So under the hand lens, you can see a whole series of lines that line up that kind of are suggestive of motion.
And we talked about how the notable dip to these bedrock layers may relate to the presence of larger, more significant faults nearby. Speaking of which, it's time to move on to the quarry site, where faults become a major part of the story. Walt arranged for us to visit this active quarry, whose owner graciously agreed not only to let us in, but to let us share some footage with you. No one should enter quarries without permission. Not only are they dangerous to you, but you could be putting someone else's business at risk in terms of liability.
Tell us another story.
Okay, so if we're looking up there, and this kind of thing is hard to interpret from afar because you can get fooled by light conditions and the color of the rock. So, you know, grain of salt here. But if this is the upper surface of the quarry wall, and then, you know, we've got a rubble layer down here, there's a pretty clear angled surface kind of contact. You can kind of see an angle thing there. And what I see is that on the right side of this, there's a noticeably darker grayer layer that kind of fills in the whole top here, and then it's a lot lighter down below. But if you go up on the left side of the fault, you can see a darker layer just filling in that upper corner, and then this what looks like the same lighter layer down below. So there's offset of maybe, I don't know, 20 feet, 15 feet there, where that bottom of that darker layer basically does this. Kind of a Z shape there.
Good explanation.
So to me, that, with the caveat that I'm not looking closely up there looking at it, that looks like a fault where, again, this side has gone up and this side has gone down.
And there's also something else confusing about this. Normal faults usually let the rock extend. So if you have a fault, if this is a normal fault, you would expect this side to drop down relative to that side. So that would be here. This would go down here. and that would go down there. So you would expect these to extend outward in the side. If the floodplain is like at that angle, you'd expect this one to be downdrop relative to that one. But what we're actually seeing in this one is that this side appears to be up relative to the other side, so that, or something like this, which is kind of the opposite motion that we would expect from the kind of fault that we would sort of most expect to typically see. But we also, there's probably some strike slip motion on this fault, so lateral like this, not just up and down. And it can be really hard to tell how much lateral motion there's been because you don't have good markers to tell how
Understand.
With layers, we can say, oh, it's gone this way. With the lateral, it's guesswork.
Yeah. I think the point is with lateral motion can fool you into thinking there's been vertical motion. Because if something is tilted, if I've got two tilted things here, if I move it sideways, notice how it now looks like this hand's above this hand, but I didn't move it vertically.
No,
if I do this, it looks like that, but I can also do this.
Excellent.
So that could be a sideways motion imitating vertical motion.
Excellent.
And that would explain why it looks like an odd fault for this area.
Tell me a story.
So you were asking how you can recognize a fault on a landscape. So one way to do that is if you're really lucky, you've got a quarry like this and you can just walk up to a face and see a fault. But more often than not, it's based on mapping. So if we look at a cross section, let's say we've got a series of horizontal bedrock layers like this. So if we rode a landscape like a river valley through here, naturally up on the hilltops, we know we see the black stuff. Go down the valley, we know we see this. Maybe down the river basin is this, right? That's how a landscape works. Now, so if you're mapping this on top, you'd be drawing a map where all the black stuff appears on the high ground and so on, right? But let's say that we had a big fault come through something like this. I'm going to erase that river valley, go back to the original one. Now let's say that a fault comes through and this gets offset. So now let's say the landscape is still the same, but there's a fault here. So let's say we got black, blocky, dotted, but let's say this side of the fault went down. Or now let's go up. So if it went up, now there's black here, blocky here, dotted, right? Because this side went up, this side went down.
Understand.
Right? So if we're mapping this now, we're suddenly going to see rocks at different elevations than they should be. So if we're on a map, we're going, wait a minute, this blocky stuff is normally only seen underground or down in river valleys. Now it's forming bluffs. If I'm walking this way as a map, I'm going black, black, black. Why did I hit this stuff? One of the easiest reasons why there's that sudden change is there's a fault somewhere. All right, so overall, we're looking at a sort of quarry wall of nice, fairly flat-bedded dolomite. You can see layers just sort of going across, except that behind us here, there's sort of a mottled zone, kind of like this, where those layers go away. You see that? And instead it's all it's rubble, it's junk, it's chunks of rock. There's just no structure to it. It's a different color. It's really noticeable, and it cuts right across the bedrock layers. So there's two explanations here. One is that it could be what's called fault gouge. We've talked about there's some faults running through here. Fault gouge is the kind of rubble you get when a fault just grinds everything to pieces. So this could just be rubble that's been ground up and destroyed by the fault running at some angle through. That's one. The other option, which I'm favoring at least initially, but I'm not going to swear to it, is that this is what's called paleokarst. Now, we're familiar with modern caves in the Ozarks. We understand that water gets into the bedrock and it dissolves away past caverns and we get these open spaces, right? Those open spaces can also fill in. A sinkhole can collapse, a river can wash sand in. There's all sorts of ways you can fill a cave back in. This also happened at other periods of time. We have modern caves in the Ozarks that probably developed over the last few million years. But there are caves that developed hundreds of millions of years ago. This rock is probably close to 400 million years old, but after that solidified, it ended up near the surface, and we could have had karst developing way back then as well. We actually see this all over the state, where you've got ancient caves that date back hundreds of millions of years that have been filled in by much older sands that washed in nearer their age than now. And if that happens, you end up with this whole, what's called fill, paleokarst. The word paleo means old, so paleokarst, old karst. So what I think we're seeing here is a very, very old cave or sinkhole feature in the bedrock that got filled in by rubble that itself solidified into rock. And now when the quarry wall exposed it, you're seeing what's basically a mold of an old cave in the rock wall. And you can imagine if we did this today, if we filled in one of today's caves and then let it solidify and cut into it, we'd see the exact same thing. You'd see a mold of a cave in the bedrock.
Understand.
That's paleokarst, and we see these all over the place in the Ozarks. Without a closer look, unsafe in these conditions, we had to leave the fault gouge versus paleokarst question unresolved.
But another quarry phase held an even more intriguing exposure that, again, we couldn't get close to. High on the second level is this overhang containing a pocket of dark layered rock that almost looks draped over underlying material. This really looked to us like paleokarst fill, an unusual fill at that, since it looks like shale, when typical paleokarst fill in the Ozarks is sand or coarser rubble. Oh, how we wish we could have gone up there! But it shows you how many neat geologic features are out there just waiting to be recognized.
So this has been a really cool little site. It's not that unusual for the local bedrock in this region, but it's so cool to see examples of different things on site, especially in a site that we've never been to before and might never see again. So we hope you enjoyed it. What about you, Walt?
Eric and Johnny have done such a wonderful job of showing me and explaining what is going on. Very, very, very thorough. Couldn't appreciate the visit anymore. Thank you so much.
Thanks, Walt. This has been great.
Delightful.
Hope you liked it too.
Site visits and other in-person outreach opportunities like this are something we'd like to start doing more of, and we're working on developing a framework for this. Check our website for more information and look for a possible future video. In the meantime, thanks again to Walt for his enthusiasm, support, and willingness to let us share his really interesting setting with all of you. We're grateful to everyone who helps support our channel through liking, commenting, subscribing, and contributing financial support through tips via Ko-fi, link below.